So you can please open the Aurora and look for what a wave motion. This definition which has been given: a wave motion arises because of the disturbance in the medium. Or throw a stone in a lake in water, it will create ripples and the wave travel like this. Okay, so that's known as wave motion. So it's a disturbance that is in the medium, created because of the vibrations of the particle about the main position, which eventually get passed on to the other particles, and that's how wave motion occurs. What are the characteristics of wave motion? You can say the first characteristics, the definition itself. The wave motion arises because of the disturbance in the medium where the particles vibrate about the main position, and these disturbances get passed on to the adjacent particle, and that's one characteristics. The other characteristics that you can say is about one particle to the other particle, there will be a constant phase difference. There will be a constant phase difference between two particles at different positions. So that is another point. The next point that you can say is the velocity of the wave can be different to the velocity of vibration of the particle. The velocity of the vibration of the particle about the main position, at the main position velocity is maximum, at the extreme position velocity is minimum. So this is the main position. So then therefore the velocity keeps on varying with time and position. Whereas the propagation velocity, which is the wave velocity, is always a constant. It's not varying. Okay, this is something that you got to remember. And you want to find the wave velocity. The wave velocity is distance by time, where it's wavelength by time period, which is frequency. So you get V is equal to lambda into mu. That's an expression for wave velocity. Whereas the velocity of the vibration of the particle, from the oscillations lesson that you write a position vector and then they get the velocity vector. We'll come back to that next. So then this is what it is. Therefore you understand the velocity of the vibration is quite different to the velocity of the propagation. Velocity of propagation remains a constant, whereas the velocity of the vibration is varying based on position and time. So other property that you can say, since it requires a material medium to explain the wave motion, you can term this as a mechanical wave, and the medium necessarily should obey the properties such as inertia, elasticity and friction. Inertia, elasticity and friction. Okay, so that's about it. That's the introduction. You can see it for the gist of it from Aurora. So next is, there are three kinds of wave. One is mechanical wave, next is electromagnetic wave, and then is matter wave. The different types of wave we come across. Let me give an example. A mechanical wave is a sound wave, or even a water wave, or we can call it a seismic wave. The earthquake, is because of seismic wave, where the actual particles are moving to and fro about the mean position in the same direction as the propagation of the wave itself. That's called mechanical wave. Electromagnetic wave, where there is an electrical and magnetic vibration E and B, which is happening perpendicular to the propagation of the wave. Then we call it as electromagnetic wave. The example for it is light wave. Next is a matter wave. A matter wave arises due to motion of subatomic particle. Motion of subatomic particle. What is a subatomic particle? Say electron, a proton, an atom, or a molecule, a neutron can all be termed as subatomic. When a subatomic particle is moving around, it will display wave nature, and those waves are referred to as matter waves. So this is an introduction, and so let me explain now about the spring model for propagation of wave in a medium, which means we are talking about a mechanical wave because it requires a medium to travel, and you can explain this by means of a spring model. Slinky experiment that you would have done in 10th standard. A slinky is a kind of a long spring-like thing in aluminium. When you push it a little like this, it compresses here, and there will be an expansion here. Then this compression gets passed on here, and here there will be expansion, and here there will be compression, and then again this will get passed on, and series of compression keeps traveling from left to right, and so then it reaches the other end. So this is how sound is also propagating. The better way of saying it is, let's take this cylinder in which one end is closed, the other end is connected to a piston. You push the piston, which means you're compressing it. You're increasing the pressure. When the pressure is increased, there will be a compression here, which is getting created. And there will be a rarefaction adjacent to it. Slowly the compression will move here, and this will become a rarefaction. This is where the compression is. And then this compression will travel like this. So you understand that there will be a compression which comes here, and then there will be a rarefaction here. In this stage here. And then this series of compressions travel from left to right when you put the pressure on it, or when you press the piston in. When you press the piston, pull the piston out, the pressure will be reduced. So what is happening in this case is like the rarefaction travel from right to left. The same case where the rarefaction tends to travel from right to left. So you can see this is compression, this is rarefaction, compression, rarefaction, compression, rarefactions. Like this, it can go on, compression, and then there is a rarefaction, and there's a compression. So this is how you can draw the diagram and say that the air molecules travel like series of compressions and rarefactions. It's the compression which moves from left to right when the pressure is increasing, as the rarefaction moves from right to left when the pressure is decreased by moving the piston. Thus, you can explain how a longitudinal wave or a sound wave is produced in air. Okay, so this explains this, the slinky model. This is called a spring model, which explains longitudinal wave. And this is explained by means of compressions and rarefactions. So longitudinal wave is always like this. Then what is a transverse wave? A transverse wave, let's take a string which is attached to a rigid wall here. You push this up, this end, hold it like this and push it up. It develops a pulse here and keeps traveling as pulse, and it keeps propagating to the right side. It's a pulse. You take the wire and move it up and down, and then the pulse will have upward pulse and downward pulse, and it could be a sinusoidal pulse. Sinusoidal pulse, which travels from left to right. So that's about how, can you see from the transverse wave, the vibration of the particle is moving up and down about the mean position, and perpendicular direction of the propagation. The propagation is happening like this, where the particles are moving up and down about the mean position. So a longitudinal wave is one where the particle is moving in the same direction as the propagation. A transverse wave is one where the particles is moving perpendicular direction of the propagation. And remember, the sound wave travels only in a medium, and transverse wave, if the light wave, it doesn't need a medium, but a transverse wave can also travel in solids. It's not that it will travel only in vacuum. Transverse wave can travel anywhere. Okay, so the properties that the medium should obey is elasticity, inertia, and friction. So let's continue with there are some definitions. As per, it's also given in Aurora, you can watch out for it. Its amplitude is the maximum displacement about the mean position. This is the mean position. The center line is the mean position. The maximum displacement, this is called amplitude A, about the mean on either sides. So maximum displacement of the particle about the mean position on either sides is known as amplitude. What is time period? Is the time taken for one complete oscillation. The time taken to complete one full oscillation. One full oscillation is this. This is one full wavelength. That's known as capital T. So next, let's talk about frequency. Frequency is the number of oscillations per unit second. Number of oscillations per second is known as frequency. Is reciprocal of the time period, and SI unit is hertz. So let's go to next. Next is angular frequency or angular velocity. Angular frequency is omega, which is 2 pi by capital T. A 2 pi is the rate of change of phase. This itself is, this 2 pi is the phase change for the whole time period. So we can say rate of change of phase. Rate of change of phase is termed as angular velocity. The SI unit is radians per second. Radians per second. Let's go next. What is a wavelength? A wavelength is the distance between let's call one wave like this, another second wave is like this, a distance between two antinodes, or a distance between two nodes, distance between this and this, it's not exactly two nodes, not two successive nodes. So let's let's say the distance between two crusts and two successive troughs can be called as wavelength. Or the distance moved by, it's that distance moved by the particle, the distance moved by the wave, the distance moved by the wave when the particle moves and completes one full oscillation. You can say this is a better definition for wavelength. The distance moved by the wave when a particle moves through one complete oscillation can be termed as wavelength. SI unit is meters. So then what is a wave number? A wave number is basically a mu bar, which is the reciprocal of wavelength. It means the number of waves present in unit distance. Unit distance, how many number of waves present in unit distance. You must have learned this in chemistry. So that's known as wave number. SI unit is per meter because it's 1 by lambda. Then is the angular wave number. Okay, I think this is enough. Then we also learn this, which is a propagation constant. Very, very important. There's something called a propagation constant, which is represented by letter K, which is 2 pi by lambda. Just memorize this. 2 pi by lambda. It's radian per meter is the SI unit. K is equal to 2 pi by lambda is known as propagation constant. Then of course is the wave velocity. I already told you what is wave velocity. Velocity is distance by time. So lambda by capital T or lambda into mu. Lambda into mu. This is the velocity of the wave. Lambda into mu. Okay. So next is let me take the next topic in Aurora. Just turn the page around. You must not do it so much in detail. You should do it like the way I am doing. Okay. So let's talk about the speed of a transverse wave. Next topic. Speed of a transverse wave. Okay, and I cannot talk about vacuum here, so I have to talk only about medium. Let's take a stretched string. And let's create a transverse wave in the string. What are the factors that is present in the string? There's a tension in the string. There's mass per unit length in the string. Therefore, the velocity with which the wave can progress is proportional to root of tension by mass per unit length. This itself, they're calling it as some m here. Let me call it as red color m, which is mass per unit length, which is known as linear mass density. Linear mass density. And velocity, there's a constant of proportionality, which is just 1. C is equal to 1. So therefore, we can say V is equal to root of T by m. Tension by mass per unit length is the formula for velocity of the stress string. Next is velocity of the wave in solids. Speed of transverse wave. A transverse wave is a topic in solids. In solids, you should remember that V is directly proportional root of eta by rho, where eta is the shear modulus or modulus of rigidity, by rho is the density, which is mass by volume. So V again is equal to C, and C is 1, so you can ignore eta by rho. That's a formula for speed in solids of transverse wave. Transverse wave. When it comes to a longitudinal wave, okay, let's go to longitudinal wave and analyze how the speed is in the case of longitudinal wave once again. Sorry guys. So hope it's recording. Yeah. So let's talk about a longitudinal wave here. A longitudinal wave, obviously you can't create it as string, no. String produces only transverse waves. So longitudinal wave are produced in gas or in air. Let's take it at standard temperature and pressure. Let's analyze the speed and what are the factors that you have in gas is K, which is the bulk modulus, and density, which is mass by unit volume. So the velocity will be equal to root of K by rho, is proportional to bulk modulus by rho. But having said that, the constant of proportionality is still taken as 1, so you can get this answer. So this is a longitudinal wave, and the speed of the longitudinal wave in gas or in air. So now the speed of the longitudinal wave in solid. So the topic is longitudinal wave in solids. In solids, the velocity will be something that you have to mug up. There will be bulk modulus as well as shear modulus. The formula is k plus 4 by 3 eta by rho is something that you got to memorize. So next is take a rod and study the longitudinal wave. In a rod, you will have Young's modulus. So velocity is equal to root of Young's modulus by rho. So that's something you got to know. Then here's where the lesson starts. The first question that can come is Newton's formula for speed of sound in air. So for the speed of sound, Newton is going to explain this. And Laplace will correct it. It's called Laplace's correction. These two questions are very important. What did Newton say? He said that velocity is equal to root of k by rho, where k is a bulk modulus in isothermal condition. He's taking gas at standard temperature and pressure, and he's taking it as isothermal. Isothermal in itself, from thermodynamics, you know that the temperature is constant. Okay, so you know that PV is equal to constant because nRT, N is number of moles, R is gas constant, T is also constant because it's isothermal. So you differentiate this as U and V, P into delta V plus V into delta P is equal to 0. From that you write an expression for P which is minus V into delta P by delta V. You cancel the V and bring it down. This, according to solids lesson, you know it's nothing but the bulk modulus K. But this is K iso because we have studied this under isothermal condition. This can also be replaced by pressure. So then it's merely pressure of the gas by density. How to find the pressure of the gas? At standard temperature and pressure is categorized as 0.76 meters of mercury by density of the gas. If supposing you're going to take it as air instead of gas, you're going to take it as air. The air's density you can consider as 1.293 kg per meter cube. And this is density of the pressure of the standard temperature and pressure. The pressure is 1.013 into 10 to the power 5 Pascal by 1.293. You calculate, you get 280 meter per second to be the velocity of the sound in velocity of sound in gas, okay, or air. Okay, so you get it as 280 meter per second. Then Laplace is coming and correcting it. He says, come on Newton, this was not to be done in isothermal conditions, is not applicable. You should have done it in adiabatic condition. Why? Because the series of compressions and rarefactions occur too quickly. Compressions and rarefaction occur too quickly, and any fast process is only adiabatic. So you should have taken PV to the power gamma as a constant, not PV as a constant. So I'm differentiating as U and V, P into differentiate V to the power gamma is gamma V to the power gamma minus 1 into delta V plus V to the power gamma into delta P, dP is equal to 0. From this, right, what is gamma P? Is minus V to the power gamma into dP by V to the power gamma minus 1 into dV. When you take this up, gamma minus gamma plus 1, it will be just V. dP by dV, bring it down, you bring the dV down, you get it as K. So thus you get a bulk modulus which is K adia, which is gamma P. So because it's adiabatic condition, instead of the velocity, thus instead of writing a K adia by rho, you can replace it as gamma P by rho. Gamma P by rho. Rho is the density, gamma is the Cp by Cv's ratio. They will give gamma in the question. Okay, so that's about it. This is what is called Laplace's correction. And when he studied this for they are given that for air gamma is 7 by 5. They calculated the entire value to be substituting the pressure and the density. They get 331.3 meter per second. They got that, and the closest value, which is in agreement to the experimental value. So Laplace's correction, these are all theories, okay, but when they did it in experiment, they got something closer to 330 only. So Newton's method is not getting a closer answer. Laplace's correction helped us to correct it. Okay, that's a very, very important question. So the next topic is what are the factors the speed is going to depend on. Let's see, one second. The speed's formula, thus you got it as root of gamma p by rho in a gas. So let's study the variation of effect of pressure. First is effect of pressure. When the pressure increases, you expect the velocity to increase from this formula, but no. When the pressure increases, the volume decreases. Density is mass by volume. When the volume decreases, density also increases. So pressure increases, density increases. So when the pressure increases, density also correspondingly increases. So velocity remains a constant. Velocity remains a constant. So velocity is independent of pressure. So let's go to second. Effect of density. Effect of density. And you know that in this case you have to compare two different densities, two different gases, one of density rho 1, other of density rho 2. And velocity is inversely proportional to density. Density is lesser for one gas. The velocity will be more for it. See, let's compare a hydrogen. Rho 1 is lesser than rho 2. The velocity will be, V1 will be greater than V2. So let's consider hydrogen. Hydrogen is less dense when compared to oxygen. Mass is 16 times, so density is also 16 times the mass of hydrogen. And so since the density is lesser here, the velocity is greater for hydrogen than that of oxygen. And it's square root of density, it's reciprocal of square root of density. So if this is 16 times, velocity of hydrogen will be 4 times the velocity in oxygen. So that conclusion you get, that's the relationship between density. The velocity and density does change. Next is humidity. Humidity. In humidity means there are water vapor in the atmosphere. The presence of water vapor in the atmosphere makes the air less denser. Less denser. Less denser means velocity is more. Velocity is more. So you know that when compared to dry air versus humid air is less denser and so velocity is more. So humidity is more, the velocity will be more. Humidity and velocity are directly proportional. Next, let's compare with the temperature. The temperature dependency, you know that velocity is root of gamma p by rho, where replace V is equal to nRT, or therefore P is equal to nRT by V. Just cancel M, considering it as 1 mole. Gamma RT by you have a volume here, and density itself is mass by volume. Volume get cancelled. So gamma RT by M shows that velocity is directly proportional to square root of temperature. As temperature increases, velocity is going to increase. So that's the conclusion about that. So next is supposing they ask you the temperature, okay, let me complete this, and then effect of wind. Okay, effect of wind, that's something very simple. If the wind is going to flow like this, the velocity has to be subtracted by the velocity of the wind. When the wind is going to flow in the same direction, the propagation of the wave is in this direction, wind is flowing in the opposite direction, subtraction. Propagation of the wave and the wind also in the same direction, V plus VW. And so we're supposing the wind is blowing like this, they take the component which is V cos theta, horizontal component will help the wind to propel even faster. So that's the about wind. And let's talk about frequency, the dependency of frequency. The velocity is independent of frequency, Okay, I hope you're clear. For a simple example, if you were to hear the sound of you're going and listening in an orchestra, okay? Orchestra, they play a violin which is vibrating at a different frequency. They play a guitar which is at a different frequency at one point of time. Two different frequencies is able to reach our ear at the same time. That itself shows that the velocity does not depend on frequency. Remember this example. Then let's go to amplitude. The speed of sound is independent of the amplitude of the sound. If the amplitude is very large, the compressions and rarefactions may cause large temperature variation which may affect the speed of sound. But generally, Only if the amplitude is very, very large, it's going to affect the speed of sound, because the amplitude is too large, there will be too much, a large compression draft fraction where the temperature changes becomes significantly large. Otherwise, it is independent. Okay, leave it like that. Okay, so now I'm going to teach you about temperature coefficient of speed of sound. Temperature coefficient for the speed of sound in air. What is this temperature coefficient? You know, velocity is directly proportional to square root of temperature with what I taught you. So supposing a temperature at a particular Kelvin is always a degree Celsius temperature plus 273, which we learnt it in conversions in thermal properties. So let's do at 0 degrees Celsius. You substitute and you find your velocity is also directly proportional to this temperature, right? So the initial velocity is therefore proportional to root of 0 plus 273. So velocity at a particular temperature T degrees Celsius will be proportional to T plus 273. So there may be a constant of proportionality which get introduced, but when you divide 1 by 2 with the constant will get cancelled. So you can do 2 by 1, which is Vt by V0 is equal to root of T plus 273. Root of T plus 273 by a 0 plus 273, which is merely a 273. So now this is V. What is V of T? Vt at a particular temperature, the velocity is V0 into, you can write this as a whole root and write as 1 plus T by 273. So it says 1 plus T by 273 with the whole root, which can be written as 1 by 2. Now applying a binomial theorem, this half can come here, V0 into 1 plus T by 2 into 273, which is basically 546. This is my velocity at a particular temperature. Okay, you can take this in if you want. You can take this in. So Vt is equal to V0 plus V0 into T by 546. Take it that side. Vt minus velocity at a particular temperature minus initial temperature at 0 Kelvin, 0 degrees Celsius equal to V0 into T by 546. And you know V0 itself is 332 meter per second. The closer to the 333 we called it now, Laplace's correction. It's actually 332 into that unknown temperature through which it's risen by 546. Will give you 0.61 T. Okay, and there is also this V0. You can bring this V0 down. You brought this V0 down. Oh no, I'm keeping the V0 there and calculating this. I kept the V0 there and calculating because I plugged in V0 to be 332. So then, therefore, a Vt minus V0 is 0.61 into T. If the for T's temperature change, it's 1 degree Celsius. Imagine it is 1 degree Celsius. A Vt minus V0 is 0.61 meter per second. The change in the velocity. So therefore, you know the change in velocity is 0.61 per unit second. And you know temperature coefficient here is change in velocity. The velocity of sound in air increases by 61 centimeter per second for every 1 degree rise in temperature. This is known as temperature coefficient. This is known as temperature coefficient for sound in air. The velocity of the sound increases by 61 centimeter per second for every 1 degree rise in temperature, and this is known as temperature coefficient of sound. Okay, just get to know this. Okay, so next topic is progressive wave. So let me teach you the displacement relation. Okay, you're going to write a displacement relation for a progressive wave. A progressive wave, which is one which progresses rightward. Don't think the particles are moving, the particle that's here comes here and then goes here. No, it's not the particle, it's only the wave created by the vibrating particles. I'll show you a video later. So a wave which is propagating in this direction. Let's take this point, this origin, let's take this distance as x. For this position, point P. we have to write an expression for the displacement, which is y of x comma t. From oscillation lesson, we know that we will write it as a sin omega t. So a sin omega t plus phi naught. From the oscillation lesson, we know this. Or it can be expressed as a sin omega t minus phi naught also. Plus phi naught or minus phi naught. So I am taking here minus phi naught for the wave which is propagating from, I am taking here minus phi naught. Okay. So first take this for a full phase difference of 2 pi. For a phase difference of 2 pi, there is a path difference of lambda. One full wavelength is also one full rotation 2 pi. So phase difference is 2 pi for path difference of lambda. What will be the phase difference if the path difference is x? So is 2 pi into x, so phi is equal to 2 pi by lambda into x. This is the phase difference, and this itself is called propagation constant k, which I taught you before. 2 pi by lambda is propagation constant, and plugging in here you get y of x of t to be a sin omega t minus kx. So thus you get this. So for a wave which is propagating from left to right, you should always write it as a sin omega t minus kx. Just memorize this. And for a wave which is propagating from right to left, you can express this as a sin omega t plus kx, because it's from right to, when the wave is progressing like this. This is for wave progressing like this. You must understand this. Okay, so coming back here, I know I can write omega to be 2 pi by capital T into small t, by k to be 2 pi by lambda into x. So from this I am allowed to take entire 2 pi out. So I'll get t by lambda minus x by 2 by, t by capital T minus x by lambda. I can also take a t out, even though there is no t in here in this expression. You can multiply and divide by t. So a sin 2 pi by capital T, you can take it out. So it will be t minus x into, I would have multiplied and divided by t, I would also get a capital T here. So like that, and there is also one more lambda which is present here. Just write it. So you can, like this, you understand that you can express it in different formats. And this lambda by t, can you see, is a reciprocal of velocity. Velocity is distance by time. So you can also write it as a into sin of 2 pi by capital T into t minus x by b. So like this it can go on. Okay, you can express it in different formats. So but the format that we require is only what is in here. This is the main format. Okay, so take that format. So that is the propagating wave, and this is traveling from, as you know, is left to right is an example I've taken. I've done all this. Right to left, you just have to replace the x to be negative, and so it becomes omega t plus kx. Okay, now this is the way you write an expression for the displacement for a propagating wave. And supposing this comes with a pre-existing phase difference, you can write this expression as y of x of t to be a sin omega t minus kx plus phi naught, where phi naught stands for the initial phase. You can always write this. Okay, so this whole thing is called the phase or total phase or argument. Then what is phi naught? Phi naught is the initial phase. What is the meaning of initial phase? Supposing we both are starting, there's a relay race going on. Okay, so in relay race itself, the first person is running from here, the second person is running from here. With regard to position, there is a phase difference. That is the initial phase itself. Okay, that's called phi naught, and so you get the total phase there. So take and write the phase. We are going to find the phase difference. Take the phase. To find the phase difference, take the phase. What is the phase here? You know, it's omega t minus kx plus phi naught is the total phase. And this is called phi in general, total phase. And differentiate this with respect to time, you will get omega dt by dt. All these components will become 0. Differentiate this with respect to position, you'll get minus k. Therefore, d phi or delta phi is equal to omega into dt, or 2 pi by capital T into dt. You get this formula for delta phi or d phi. You can write delta also, it's your wish. Okay, so how you write is like this is 2 pi. And here a d phi can also be written as minus k into dx. So you get an expression delta phi is 2 pi by capital T into delta t. You get a delta phi to be minus k into delta x. So with respect to, you get the change in the position with respect to time, and also change in position with respect to position. So you do like this and find the phase difference. There are two different ways in which we can find the phase difference. Taking that phase value, just that in the bracket, this one, and differentiating. So now you know this is the, okay, now go back. Okay, this is what it is. Now let's find the, you know how to find the phase difference with respect to time and with respect to position. Now let's find the particle velocity. Particle velocity. Okay, this is about particle velocity. How do you represent the position of the particle? Y of x of t, I just taught you, represent as a sine omega t minus kx plus phi naught. You can ignore that. Okay, to find the velocity you can differentiate it. It will be a omega cos omega t minus kx. You all know differentiation. If you know mathematics well, you will understand what I am saying. By chain rule, the omega will come again. So this is what it is. But you can't compare a sine with a cos. You can only compare a sine wave with a sine wave. So you know you can write this as sine of omega t minus kx plus pi by 2, because velocity in physics is always ahead of the position by 90 degree. So this is one way in which we can express velocity to show that velocity is ahead of displacement, which is this position vector by 90 degree. However, just leave it like this. This is what it is. This is another way which you write. It's minus a omega sine omega t minus kx plus pi by 2 is another expression. Show that velocity is ahead by 90 degree. Okay, this is the second. This is the first equation. This is the second equation. So now you got this velocity where you differentiated with respect to the dy with respect to dt is what you did. That's why you got a coefficient as omega. Now what you do, you see, take the same thing and differentiate with respect to dx. With respect to position, you get minus ak. You get minus ak into cos omega t minus kx, because x will get differentiated as per chain rule and it will become minus. So now take this and this, which is that is a dy by dt by a dy by dx. Take the first equation, this one, and what is it? Differentiated value with respect to time and differentiated value with respect to 3 and 4. So take 3 and 4 and divide it. You get a omega cos omega t minus kx by minus ak cos omega t minus kx. Can you see a and a get cancelled? The cos and cos get cancelled, become minus omega by k. Omega itself is 2 pi by capital T, and k itself is 2 pi by lambda. 2 pi get cancelled, you get minus lambda by t, which is nothing but the velocity of the wave. Thus you took the particle's velocity with respect to time and particle's velocity with respect to x and divided, you get the ratio to be the velocity of the wave itself. And you know the particle's velocity does change with time and position, but the wave velocity is a constant. Okay, so that's about it. And therefore you know that the particle velocity with respect to time is a wave velocity multiplied by dy by dx, which is the slope of the position, slope of the y with respect to x, or a displacement curve at that point. Okay, so then that's about it. And let's talk about particles acceleration. Particle acceleration, take velocity and differentiate it once again. Where is velocity? Is this is the second equation here, v of xt. You know v of x of t is nothing but a omega. It was a cos omega t minus kx. Cos omega t minus kx. This was an expression for velocity. And take it and differentiate it again with respect to time. You must do, not with respect to position, because this acceleration you will get Cos will get differentiated minus sign, so minus a omega square sine omega t minus kx, because here omega t minus kx, because you know you're differentiating this time once again, so you get one more omega. And this you can write it alternatively to remove the negative sign. You can write a omega square sine omega t minus kx plus pi, to show that the acceleration is pi by 2 ahead of velocity and pi ahead of the position. So therefore the conclusion is velocity is ahead of the displacement by pi by 2, acceleration is ahead of the displacement by pi. Okay, so that's about it. The maximum amplitude is this always, which is the coefficient of the sine. Okay, so that completes it. And let's go to the next topic that I taught you today is a boundary effect. Let's go through boundary effect. Okay, supposing you have a rigid boundary here, and you're taking a stretched string and you're pulling it up, then you get a pulse like this. This pulse travels till the wall and reaches the wall. As it reaches closer to the wall, it comes and reaches it like this. It's going to exert an upward force on the wall, but every action has an equal and opposite reaction, so it comes back. When it comes back like this. This is the returning pulse. This is onward journey and this is the return journey. There is a phase change. Can you see? It's completely inverted. So there is a phase change of phase difference of pi radians when it's hitting a solid boundary. Okay, but when it is hitting say take a rod and put a ring, this moves up and down. Okay, so when a pulse comes in here and falls on this, okay, it is not a rigid wall for it to exert an equal and opposite reaction. So what happens? That it gets merely reflected and comes back. This is onward. The ring is going to just return it like this and it comes back like this. That's all. Okay, so there's no Newton's law, and so there's no phase change. The direction is getting reversed, but no phase change in the case of a ring. So that's something you got to remember. Okay, so that's what happens. And let's write an expression for this. Okay, so the incident waves going from left to right, you know, y of x of t, how do you write? You write a sine kx minus omega t. Correct? But in this case, can you see the y value is becoming negative? The x is also, okay, omega t minus kx, sorry. Is omega t minus kx is how we express. But you know, the x is also reversing its direction. The y value is also negative. So for the return wave, you should write minus a sine omega t plus kx, because x is also reversing, y is also reversing. So whereas in this case, the y is remaining always positive, only x is reversing. So the onward wave is equal to x a sine omega t minus kx. Returning y of x of t is a sine omega t plus kx. Only x is getting reversed, the y is remaining to be the same. So that's the explanation for boundary effect. It's got a solid boundary and open boundary. This is called open boundary and this is called solid boundary. Okay, develop your own notes with this. So next is there's no phase change. Here it's got no phase change. Okay, let's go to next, superposition of waves. Superposition. Two waves are going to come together and get added. Okay. So for superposition of wave, a number of waves can be traveling in a medium. But only thing is they all have to travel in the same direction. So then you know you will have y1, y2, y3 or the individual displacement. And so y can be y1 plus y2. The net displacement can be added till yn. So a principle of superposition of waves states that when a number of waves travel through a medium simultaneously, the resultant displacement of any particle of the medium at a given time is equal to the algebraic sum of all the displacements of the individual waves. So now in this lesson we are not going to have number of waves, we are going to talk about only two waves superimposed, two identical pulses. Okay, so let's talk about superposition in general. You have a crust and a crust coming together, it will result in a bigger crust. A crest and a trough coming together, it will result in destruction Okay, so it's as simple as that. Okay, that's how superposition happens. So let's take a wave which is like this and like this. Both of them are having crest and crest in the same position, so it will result in a bigger amplitude wave. But when you have two waves which are superimposing, which has got a crest and which has got a trough, then obviously it will cancel out and you will not have any resultant here. That's something you should know in superposition. So that's just one line, you don't have to learn more about it. Now I'll tell you what is interference of wave. They'll ask you to define what is interference of wave. It's nothing but two waves having the same frequency, traveling with the same velocities, traveling in the same direction, superimpose or superpose on each other. They term it as, gives rise to a resultant wave, that's called interference. So next let's talk about what is a stationary wave. See, the station in this, it's traveling the same direction. Here, so it's about two waves having same frequency, same velocity, same direction. Stationary wave, same frequency, same velocity, opposite direction. That will give rise to stationary wave. So third one is what is beats. Beats is this when two waves of slightly varying frequency traveling with the same velocity and same direction give rise to beats. Okay, they superimpose, give rise to beats. Okay, let me talk about what is a stationary wave. I'll show you a video which explains very clearly.
Here's a string that's vibrating.
Let's see
up and
this.
down because there's a
This person in here is trying to vibrate this string.
And look, the string is going up and down like a standing wave.
Can you see that there are one full wavelength that he has produced on the left and right?
With different frequencies.
He's adjusting
so this
and changing the frequency around of oscillation. He gets one half wavelength. Just observe how he's doing
slow-mo, you can actually see that up
Then
and
I'll
down
explain.
vibration of the string. The crests and troughs don't move across. That's why we call it a
Again, he's
standing or
created. Can you
stationary
see?
wave.
There's a standing wave which
There
is
are
created.
different ways to vibrate
You
this
can see the
string
entire
to make it
wave,
look
both the
different.
up and the down.
And he's drawn
That's
some
called
of
a
the
standing
shapes on
wave
the board here.
or a stationary wave.
So this is a really long wave because you can only see half. You don't even see the other half where it goes up and also then goes down. So this is
So
a huge
let's go a little
wavelength.
forward.
So this is a huge wavelength. When we turn up the speed of this vibrator and make the frequency increase, while a higher frequency means a smaller wavelength. So
Can you see he has created
in fact, the wave is
two
short enough that we can see just
segments,
the full wave.
and now he's
And
created
here's an
three
even
segments,
shorter wavelength.
which is like a 1.5. Two
This
segments
wave
make one
is so
wave.
short, so
One full
small in
wavelength.
length,
Three segments.
that we can
Like that
see
he is
one
able to
full
vary the
cycle here,
frequency of
and then
oscillation.
another half cycle here.
As getting different standing waves here.
But how does standing
Now I'll
waves
tell you what is a progressive
form?
wave. You see,
I mean, if I start this
the green
thing
color
oscillating,
points you just observe.
the wave travels
Yes,
across.
this is a
There's
progressive
motion of
wave. It's
these
progressing
crests.
from left
They
to
move
right.
to the right. It's
But
not
still the
standing,
green
it's not
points is
stationary.
there only, but moving up and down
Watch
about the
it
mean
longer.
position. The green point is not moving forward.
Standing
The
wave
wave
is
is appearing to move
And
forward.
it's forming and moving
It is
across
giving an
the
appearance
screen.
that the wave is progressing forward while the particle
So
is just
something
moving
happened
about
to
to and
produce a
fro the mean
standing wave.
position.
Let's watch again.
Once it goes to the right end and then
Here's the
comes
initial
back,
wave. It travels
by
to
touching the
right.
rigid surface,
And
if it's
as
going
it
to come
travels to the
back,
right, more waves are
it
coming,
will start
also
creating
moving to the right. Then these reflect.
a stationary wave. You see,
And
once it
consider
comes
the
back,
reflection
now
is what
it will
creates
create
the
a
standing
stationary wave.
The reflection is moving
Yeah, can you
across
see
the
now?
screen. You can see
Yeah,
it.
it's not progressing
here,
anymore.
And now it's like here.
Once the returning
Standing
wave comes and
then
touches
here,
the onward
here's the standing
wave,
So the
wow.
reflection travels across, creating the
So
standing
two
wave.
progressive waves in
You
the
can see
opposite
it
direction
across
gives
the
rise
screen
to
as the
stationary
standing
wave.
spreads.
The points that you have to note
Let's
in a
watch that
stationary
one more
wave
time.
is actually the
There's a
ones
wave traveling
progressive wave, the particle, every particle is going to
And
be
then
a mean position, then extreme
There's an
position, then
identical
mean position.
reflection.
Is having the
The two
maximum amplitude every
interfere.
particle.
That's what
Whereas
makes
in
the
a
standing wave.
stationary wave, if you see, each particle has its own amplitude. Okay,
Let's
I'm sure you
inspect that a
understood
little
this.
closer.
So with this as an
We've said that
example,
standing waves-
I'll just continue to write my notes and you understand. So basically, you understand the difference between a progressive wave and a stationary wave. It's a common question that comes in every paper. A progressive wave, you notice that each particle is just vibrating to and fro about the mean position, and I can see it better. The part in this whichever particle were in the nodes weren't even moving. If you noticed, the ones which were in the node, it was just this part, this is going up, this is coming down, this is going up, this is coming. What is in nodes remain to be in nodes. Okay, and each particle will have different amplitude when it goes up and down. But here every particle reaches the maximum and minimum amplitude, reaches maximum amplitude and minimum amplitude and crosses the mean position. After crossing mean position, whereas in this every particle has its own little amplitude. Every particle has its own amplitude. It's not always the same. The maximum displacement about the mean position is not always the same, and also some particles at the node does not even move. Particle at the node will not even move. They remain stationary. So then what else can we say? Okay, if you see, this is one segment, this is another segment. The particle in one segment will vibrate in one phase. The particle in the adjacent segment will vibrate in a different phase. In the case of stationary wave, all particles in one segment, when I say one segment, it's in this half, is all in single phase, Whereas here, every particle will have a different phase, correct? Every particle, there will be a phase difference in the case of progressive wave. So I'll explain this furthermore when it comes to these are the two things that strikes me. So then the disturbance travels forward. In this, the disturbance travels forward with a definite velocity. The vibrations is resulting in a disturbance which is traveling forward. Here the disturbance remains confined to a region. So here the disturbance, just write a note, the disturbance is progressing forward. Here the disturbance is confined to a specific region. And each particle is exerting a simple harmonic motion, that is moving to and fro about the mean position with the same amplitude. That's the first point that I wrote here. Whereas in here, the points of the node will remain stationary, all other particles will move about the mean position but with varying amplitude. Here, the next point is there is a continuous change of phase between one particle and the next. Every particle has its own phase or continuous change of phase. But here, all particles in one segment has the same phase. The particles in the medium, okay, all the particles in one segment are vibrating only with one phase. Only the adjacent segment will have another phase. Okay, so then no particle is at rest. Whereas here the particle in the mean position, particle at the nodes are always stationary or at rest. There's a flow of energy across every plane along the direction of, there's a flow of energy that's happening here. A flow of energy that's happening here along the direction of propagation. Here energy is confined only to one region. Energy is confined only to that region. And I think these points are enough. You just understand these and write these points, more than sufficient. I've given some extra points, I'm not going to deal with it. Okay, so let's go to, so you understood what is a stationary wave and what is a progressive wave. So let's now do this, the analytical treatment of stationary waves. So you know two independent stationary waves. I'm not talking about two stationary reflected waves. I'm talking about two independent. One is a sine omega t minus kx. Another independent one is a sine omega t plus kx. Because they're two independent, I'm not inserting a negative sign here. I'm not inserting a negative. I'm supposed to, right? Because if it's returning wave, if this is the onward wave and this is going to be a returning wave. So I'm just considering it to be two different waves. Consider two sinusoidal waves of equal amplitude and frequency traveling in opposite direction. And the net displacement is y1 plus y2. You write a into common sine omega t plus kx plus sine omega t minus kx, adding both of this. You get a sine a plus b plus sine a minus b is 2 sine a cos b, 2 sine omega t cos kx with an a. So a 2a cos kx can be brought forward and a sine omega t can remain here, and this can represent your maximum amplitude. So thus you take, this is your net displacement. You take this maximum amplitude and write it separately, and this is where we are going to do the analysis. A maximum amplitude, this expression is 2a into cos kx. At the mean position, you know the amplitude is going to become 0. If this got to become 0, the cos kx has to become 0, and cos becomes 0 at odd positions here and here, which is, it's actually a pi by 2, a 3 pi by 2, a 5 pi by 2, a 7 pi by 2. Therefore the general formula is 2n plus 1 by 2 into pi. And so instead of k, you can write 2 pi by lambda into 2 pi by lambda into x is equal to, you can just continue to do it as 2n plus 1 by 2 into pi, where pi and pi get cancelled. You can write an expression for x. So you can cancel the pi and pi, you get x. Therefore you get your x. And what is your x here? It's 2n plus 1 by 4. Bring the 2 down, yeah? Into, there's also lambda, which gets multiplied like this. So put n is equal to 0 here. You get x to be lambda by 4. So now my pen is not writing, I'm sorry. Lambda by 4. Put n is equal to 1 and so on. Put n is equal to 1, you get x is equal to 3 lambda by 4. N is equal to 2, you get x is equal to 5 lambda by 4. Subtract and see 3 lambda by 4 minus lambda by 4 will result in a 2 lambda by 4, which is lambda by 2. So the distance between any two nodes is always lambda by 2. Okay, and so let's do for maximum position. For a maximum position, which is maximum amplitude. That was for minimum amplitude. Maximum amplitude, you know that amplitude's formula is 2a cos kx, where cos kx itself should be plus or minus 1. For this to achieve, you know, it achieves at 0 or pi, so you can call it as 2n pi. So you write kx is equal to 2n pi, where n is equal to 1, n is equal to, yeah, so you get, instead of k, you write 2 pi by lambda and x is equal to 2n pi, where pi and pi get cancelled, and so x is equal to 2n into lambda. 2 and 2 also get cancelled, is it? So you get x is equal to, so kx is equal to 2n pi, x itself is 2 pi by lambda into x is equal to 2n pi. No, should I write, it's not 2n pi, it's just n pi. What did I write here? It's just n pi, because it can be 1 pi, 2, it can be 1 pi, a 2 pi, a 3 pi, a 4 pi, so it's n pi, sorry. So equating it to n pi, 2 pi by lambda n pi, pi and pi get cancelled, x is equal to n lambda by 2, put n is equal to 1, don't put n is equal to 0, because you already put n is equal to 0 to get the previous one, which is node, so obviously this is going to result in anti-node. So x is equal to lambda by 2. When n is equal to 1, you get x is equal to lambda by 2, n is equal to 2, you get x is equal to lambda, and so on. So these are the positions of antinodes. Thus you get the positions of antinodes. Therefore the conclusion is Antinodes are occurring at 0, lambda by 2, lambda, 3 lambda by 2, dot dot dot, and nodes are occurring at x is equal to lambda by 4, 3 lambda by 4, 5 lambda by 4, dot dot dot. That's the conclusion here. So make sure you write this, and that's the analytical treatment. And by the analytical treatment, you understand what is the distance between two consecutive nodes, what's the distance between two consecutive antinodes, etc. Okay. So next is the characteristics of stationary waves. I just told you, I just explained many other examples also. Be very clear till here so that we can continue with the lesson next class. Okay.